In this tutorial, we will be discussing the Arrhenius Equation, which includes the effects of temperature and collision on reaction rates. According to the collision theory in kinetics, there are a couple criteria for a reaction to occur. One is to overcome the thermodynamics, and the other is kinetics, including the activation energy and the correct collision orientation. In a chemical reaction, bonds are broken and new bonds are formed. Molecules can only react if they collide with each other. Furthermore, molecules must collide with the correct orientation and enough energy to cause the bond to break and to form a new one. So for instance here, we have two molecules that are colliding. Notice that the green ones are facing each other. This collision is allowing the reaction to occur. However, if it's not colliding in the right spot, no reaction occurs and they still stay the same. Collisions in which these two conditions are met and therefore lead to the reaction is called effective collisions. The higher the frequency of effective collisions, the faster the reaction rate. When two molecules have an effective collision, a temporary, high-energy, unstable chemical species is formed, called the activated complex. For most reactions, in order for a reaction to take place, the reacting molecules must collide with each other. Once molecules collide, they may react together or they may not, depending on two factors: whether the collision had enough energy to break the bonds holding reactant molecules together, and whether the reacting molecules collide in a proper orientation for new bonds to form. It is helpful to visualize energy changes throughout a process of the reaction coordinate diagram, like this one for the arrangement of methyl isonitrile. This diagram shows the energy of the reactants and the products. So the reactants are on the left-hand side and the products are on the right. And therefore, the delta E is the difference between those two. The high point of the diagram is the transition state. The species present at the transition state is called the activated complex, which we mentioned earlier. The energy gap between the reactants and the activated complex is the activation barrier. In other words, there's a minimum amount of energy required for the reaction, and this is called the activation energy. E sub A is the abbreviation for it, and you're going to see that come up a lot. Just as a ball cannot get over a hill if it does not roll up the hill with enough energy, a reaction cannot occur unless the molecules possess sufficient energy to get over the activation energy barrier. So, as we stated before, there is an energy barrier for almost all reactions. The activation energy is the amount of energy needed to convert the reactants to the activated complex. So the activated complex is on the top here. And those hold the transition state where the molecules are actually transforming. The activated complex is a chemical species which partially broken and partially formed bonds are in existence. They are always very high in energy because of the partial bonds. For a collision to lead to an overcoming the energy barrier, the reacting molecules must have sufficient kinetic energy so that when they collide, they can form that activated complex. So not only do they have to be oriented correctly, notice that those are not hitting it the right amount on the right side of it. They also have to have enough energy in order to do it. For a collision to lead to overcoming the energy barrier, the reacting molecules must have sufficient kinetic energy so that when they collide, they can form the activated complex. This is the Maxwell-Boltzmann Distributions. Temperature is defined as a measure of the average kinetic energy of the molecules in a sample. At any temperature, there is a wide distribution of the kinetic energies. So all of these down here are all at different kinetic energies. Generally, as temperature increases, so does the reaction rate. This is because K is temperature dependent. K, remember, is the rate constant. Which is different for every reaction at given temperatures. As the temperature increases, the curve flattens. Notice, here's the lower temperature, here's the higher temperature. This is actually further to the right because there's more kinetic energy, but it's also lowered because it's more spread out. Thus, the higher temperatures, a larger population of molecules has a higher energy. Notice that when it reaches the activation energy point, there's more molecules on this side. If the dotted line represents the activation energy, then the temperature increases, so does the fraction of molecules that can overcome the activation energy barrier. As a result, the reaction rate increases. This fraction of molecules can be found through the expression E to the EA over RT, where R is the gas constant and T is the temperature in kelvins. Svan Arrhenius developed a mathematical relationship between K, the rate constant, and the activation energy, where A is the frequency factor, a number that represents the likelihood that collisions would occur with a proper orientation for the reaction. Taking the natural logarithm of both sides, the equation becomes this, which actually matches up very nicely to the slope-intercept equation. Therefore, K is determined experimentally at several temperatures, where activation energy can be calculated from the slope of a plot of ln of K versus 1 over T. The steeper the slope is, the greater the activation energy is. Over the same temperature range, the reaction with the larger activation energy will change at a greater rate than the reaction having a smaller activation energy. Molecules need a minimum amount of energy to react, which is defined as the activation energy. Changes in temperature result in a change of the reaction's rate law constant K. There is a direct correlation. Arrhenius investigated this relationship to show this. Remember, this is exactly what we just said 5 seconds ago. A is a factor called the frequency factor. T is temperature in kelvins. EA is the activation energy. R is a gas constant with energy units. They specifically used this R constant rather than one that has atmospheres or something like that because of the fact it has joules in there. The proper orientation results when the atoms are aligned in such a way that the old bonds can break and the new bonds can form. The orientation factor, which is, it looks like a P, but it's actually a Greek symbol rho. The molecules must have the correct orientation to react properly, and we've discussed that with pictures earlier. The proper orientation results when the atoms are aligned in such a way that the old bonds can break and the new bonds can form. The more complex the reactant molecules, the less frequently they will collide with the proper orientation. The collision frequency, which is this Z, represents the fraction of reactant molecules with sufficient energy to make it over the energy barrier. The higher the energy barrier, in other words, the larger the activation energy, the fewer molecules that have the sufficient energy to overcome it. If you have one set of temperature and rate law data points, the following forms of the Arrhenius equation can be used. So if all we have is one temperature and 1K, we're going to need to use this equation. However, if you need to solve for the activation energy, you'll be wanting to use this one, where you have two data points. So you have two T's and two K's. Let's do a practice one of these. Determine the activation energy of this reaction. Notice we have two temperatures and we have two rate law constants. We are going to be using ln of K2 over K1. We're going to be comparing these two. E of A over R, 1 over T1 minus 1 over T2. All you really have to do at this point is plug the numbers in. So ln of K2 is 567 over K1, which is 2.57. Activation energy is what we're looking for. R is 8.314. One over T1 is 701. 1 over T2 is 895. So 567 divided by 2.57 is 220.6. E sub A, 8.314 joules, kelvins, moles. Notice that for the K's, the units canceled. I didn't write down the units. 1 over 701 Kelvin comes out to be 0.00143 kelvins to the minus 1 minus 0.00112 kelvins to the minus 1. ln of 220.6 is 5.40. Subtract those numbers out, it comes to be 0.00031 kelvins to the minus 1. Notice that the kelvins cancel out when we divide that out. So I'm going to multiply both sides by the 8.314. And we're left with joules per mole. Divide both sides by 0.00031. The activation energy comes out to be 144,727 joules per mole. Because it's significant figures, we want to have 3 sig figs. So we can either say 1.45 times 10 to the 5th joules per mole, or you can say 145 kilojoules per mole. Both of those are technically correct. And that is how the temperature and the collisions affect the reaction rates.